Alright, I did say on a separate video that we were going to talk about composition of functions. So this is continuing 2.8, but now we're just going to focus solely on composition, just because this topic is big enough on its own to have included in everything with just talking about the operations or the combination of the functions. Alright, now composition has its own notation that's very important. So I'm going to write it down here. And its notation uses, I'll be very careful, I'm writing it big because I don't want it to look like a closed, like a multiplication symbol. Because again, normally, if you look at your book, it's not going to look that big. But the idea is that symbol here means composition. What does composition mean? You can think about it as, if you ever seen when there's an egg inside of another egg and then you open the egg and there's a smaller one. Or you've probably seen the example where some people try to play a trick on someone for Christmas, where they have this humongous box and then they open that box, there's a smaller box inside, and then a smaller box inside, and then another smaller box inside. That's sort of the idea of composition. What it does is you do plugging in of functions. So you can think about it as, what would happen here, it's f, but now before, when we were looking at the operations of functions, we ended up writing f of x plus g of x, or f of x minus g of x. What happened here, it's f of g of x. So you can see how g of x is being plugged into f of x. If we had switched the order around, that means f of x would be plugged into g of x. You might also see this notation. So one more time, you might see this as written slightly differently depending where you see it. But scratch that. But that's the idea. And we can also talk about domain when it comes to compositions, just like how we did domain with operations. But let me just jump into examples. That's hopefully a good way that's going to help us understand these problems. And just like the last time, I'm going to write a few different functions. So let's say we have f of x is equal to 2x minus 6. And then we have g of x is equal to 1 over x plus 4. Hopefully you can see that. Now, let's try doing both. So we're going to try to find the first one. We're going to try to find is f of g of x. So again, it's really important to note that that's, even though it looks like a closed circle, that's not a closed circle. There's a hole in between. If I were to fill that in, that would look like multiplication. This is not multiplication. It's like saying fog, so it's like an O there with that. And there's still, again, it's kind of hard to see the hole. I did that too close. But what this is telling us to do is to take g of x and plug it into f of x. People like to do this different ways. Sometimes what they like to do first is already, before they plug it into f, they already like replacing g of x, because I know g of x is equal to 1 over x plus 4. So 1 over x plus 4. So 1. Now, that means for my f, which is 2x minus 6, everywhere I have my x, I'm going to replace it with that 1 over x plus 4. And that's what composition is doing. I'm plugging a function into another function. So you can see how the g of x gets plugged in everywhere you had an x. For f of x, so this x and that x, I replace that with 1 over x plus 4. But here, I can try to simplify this left-hand side. And I can do that by just multiplying it. If you ever think about when you multiply fractions, you multiply numerator with numerator, denominator with denominator. But the denominator for 2 right now is 1. So that's going to simplify to just 2 over x plus 4 minus 6. And here, you can try to find the domain of this. Again, if you want to combine this fraction into 1, you can. But just looking at this function at first glance, when I'm thinking about the domain, again, this, whatever this is, I can subtract it by 6. It's not going to have an effect in my domain because the domain is a set of all x coordinates. And that's what I want to watch out for. And remember, the only two functions that we have restrictions for so far is for a rational function, meaning when we're dealing with a fraction, or a square root. So a square root, you don't want to have 0 in your denominator. For a fraction, you don't want to have, for a square root, you don't want to have negatives inside the radical. For a fraction, you don't want to have zeros in your denominator. I'll say that one more time. For square roots, we don't want to have negatives inside of the radical. For fractions, we don't want to have 0 in our denominator. So here, I notice that it's not about x can't be 0, it's I don't want my denominator to be 0. So here, I don't have to try to come up with a formula to find when it's 0, like how we did in this example. Here, I know x plus 4, what value of x will make 4 into a 0? And I know that I don't want to use negative 4. I can do that by observation. So when I'm doing my domain in set notation, just like before, everything works but this negative 4. So that means it's x such that x is all real numbers. It just cannot be negative 4. For interval notation, it's, if you think about a number line, we're excluding 4, but everything above it is okay and everything below it is okay. But with interval notation, we just made 2 intervals now. There's one below that from negative infinity and stops at negative 4. And then there's one that starts at negative 4 and that continues to infinity. So you have your closed parentheses and you have union. So you have to just union them together. But this is saying the same thing. So either one is perfectly fine. But now, let's try to find, so I'm going to close this off. Let's try to find the opposite, or the reverse. G, I'm going to make that O a little bit bigger, of f of x. Now what's happening here is that we're going to take the f and now we're going to plug it in to g. So we can do that now. I can do g of, and then whatever f of x is, I can plug that in now, which I know f of x is 2x minus 6. So what that means is everywhere I have an x for g, I'm going to replace it with this 2x minus 6. And I know g is equal to 1 over x plus 4. So that's going to look like 1 over, and wherever I have my x, I'm replacing it with parentheses plus 4. And in those parentheses, I'm going to include, or in that parentheses, because that's where my x used to be. So the x for g of x and the x here for what g of x is being replaced with f. And f is 2x minus 6. Now, if I try simplifying this, I'm left with 1 over 2x minus 6 plus 4, which leaves me with 1 over 2x minus 2. Now here, if I want to find the domain, I have to ask myself, what value of x, when I multiply it by 2, it's going to cancel out with that 2. So it ends up giving me a 0. And I can do that with, so let's say the domain. I know here, I do not want this to be negative 1. Because if it's negative 1, I know, sorry. I don't want it to be positive 1. Because 2 times 1 is 2, minus 2 would give me 0. So then when I'm writing the domain, when I do set notation, that's going to be x such that x is all real numbers. It just cannot be equal to 1. I'll close my parentheses. And now when it comes to interval notation, interval notation, if I look at a number line, I'm excluding 1, but everything above it is okay and everything below it is okay. So there's 2 intervals, from negative infinity to 1 and from 1 to positive infinity. And remember, we always put parentheses around infinity, and there's an open circle at 1. I put parentheses around both ones, but then I have to union those 2 parts together. So let's look at another example. So maybe we get the hang of what's happening in this composition of things are getting plugged into each other. So let's look at this next example. So we're going to find now, we're going to find m of p of x where m of x is equal to 1 over x minus 5 and p of x is equal to the square root of x minus 2. So what this m of p of x means, m of p of x, it looks like mop in this situation. It's p of x is going to get plugged into, maybe a way to remember this is it's always going to have that same order. M is always going to be on whatever's on the left is going to be on the farthest left, and then whatever's on the right is going to end up being plugged into p of x. You might see this, let me show you a different sort of example. Let me move this for a second. Because sometimes you can be dealing with f of g of, let me write that again, just so you guys can see the O part, g of h of f of g of h of x. Again, it doesn't just always have to be 2, it could be 3. You can look at 4, 5, just depending how many you want to plug into each other. But the order always stays the same. The one on the farthest left is always going to be on the farthest left. And then you open parentheses, and the next one on the right is going to be here. And then same thing, you get parentheses again, and then you have your H. And then there's nothing else anymore. So then all that's left is just the X part. So it's going to be H of X. And then you have to close this parentheses. And then you have to close that parentheses. And it all just gets plugged in that order. You have to remember the parentheses part. Again, there could be a K of N of X. Same thing. The order, the K is going to be on the farthest left. And then it's going to be the H. Since there's nothing else, then that's when you include the X. Not the H, it's an N. It's supposed to be N. And then you want to make sure you close that parentheses. So it's just you work from left to right, and that order always stays the same. Maybe just, hopefully that helps a little bit with trying to remember when we write this notation, what does that mean? Again, a big important part is being able to recognize that that's not multiplication, that's not an O. You're going to see in your book, it's probably more like this. Just to be a little more precise. It's probably a little smaller. It'll probably look more like that. Not mop. There'll be like a smaller O there. But they mean the same thing. So what's going to happen here is where I have my P of X, it's going to be replaced by the square root of X minus 2. Because I'm plugging P of X into M of X. So everywhere I have an X for M of X, which is this, I'm going to replace it with this square root of X squared. So this is equal to 1 over, and again, wherever I see my X, I like putting parentheses just in case if there's any distribution or anything products going on. I always like to put my parentheses to remind me I'm plugging in to this problem. So now when I simplify this, I'm left with 1 over the square root of X minus 2 minus 5. This is what M of P of X is. I can't combine these together anymore because this is a square root and that's a constant. You can't combine them together. But let's say if you were asked to find the domain, now here is where you have to be careful. Again, there is procedural approaches to this, but I prefer if you sit and put a little bit of thought into it. Right away, the first thing we have to notice is there's a square root. So once we see a square root, we automatically know you don't want to have negatives inside. But at the same time, there's an entire denominator, meaning I don't want this to be 0. And the only way for this to be 0 is for this square root to simplify to a 5. Because I know 5 minus 5 will give me 0. So I want to think about, well, what value of X is going to end up giving me when I subtract it by 2 and then I take the square root of it, is going to give me a 5. Again, that's a lot of thinking there. Something you can try to think of first is, well, what square root gives me 5? And I'm going to put a note of that over here on this side. What square root, or maybe I'll do it here, put the note here. What square root gives you a 5? Instead of thinking what value of X minus 2, then you square root, it gives you 5. What square root is equal to 5? Because I know if I get 5 minus 5 will give me 0, and that's not something I want. Well, I know the square root of 25 gives me 5. And that's something I don't want to have. So then that gets me thinking, well, if I have the square root of 25, I don't want that to happen. And then when I look at this square root, now I have something to reference to. What value of x, when I subtract it with 2, is going to give me a 25? Because when I take the square root of that, it's going to end up giving me a 5, which I don't want. And I know that 27 minus 2 will give me 25. Again, the idea is because I don't want to have 0 in my denominator, and I know if somehow this entire square root simplifies to a 5, I'm going to end up getting 0 in my denominator. And the only way for this to simplify to a 5 is if x is 27. So again, you see that here. I'll plug it in. If x is 27 minus 2, that's going to give me the square root of 25, which is equal to 5. And then that's going to subtract with that 5, which would give me 0. So I don't want 27. But at the same time, the square root is still part of this function. And I know I don't want 27 because it makes the denominator 0. But it didn't make the square root undefined. I ended up getting 5 out of that square root, which is perfectly real number. I still now need to think about the square root, because the square root, you don't want to have negatives inside. So this is where finding the domains of these are a little tricky, especially when the only two functions we've seen have restrictions are fractions and square roots. So when we're doing compositions of them together, it gets a little tricky on how you determine the domain. But again, you want to step back and think. Same as this, I don't want my denominator to be 0. So that means if the square root here gives me a 5, that's going to make 0, and I don't want that. The only way for this to become 5 is it has to become the square root of 25. The only way for this x minus 2 to become the 25 is it have to be a 27. And that's something I don't want to do, because once that happens, you end up with the 5, that will make your denominator 0. But at the same time, that doesn't mean everything works. I'm not going to say the domain is all real numbers except 27. Because if I plug in 1 in here, 1 minus 2 is going to give me negative 1. So this is what I'm saying. If I plug in 1 minus 2, that's going to give me negative 1. Which I know that's equal to I, but that's not a real number. That's a complex number. So it's not just all numbers are satisfying this function. I know for sure 27 doesn't work, but there's a lot of other numbers that don't. Because remember, we don't want the radicand to be negative. So that means this x minus 2 has to be greater than or equal to 0. We've always said that. So now I'm going to simplify this so I can see exactly. I want to isolate x, because then that's going to tell me what x values am I allowed to use. Now this is saying, so let's say if I draw a number line, this is telling me that anything equal to 2 and bigger than 2 is perfectly okay. But this part here is telling me that, let's say this is a 2. This part, let's say 27, blah, blah, blah. There's like a bunch of numbers. And then eventually you get to 27. This overall function wants an open circle at 27. Again, it will have no problem with any other numbers. It just has a problem with 27. But then the square root has a problem with the numbers that are smaller than 2. So a way to satisfy both of these two ideas, in terms of set notation, this is where set notation will be a little tricky to do, because you have to be able to write you have to get creative with how you write it. So it's similar. We're not going to say all real numbers because, of course, there's a lot of numbers that don't work. But from 2 all the way above, all of them work except 27. So a similar idea, we can say that x is all the values that are 2 and bigger than 2 except 27, because the only one that's not included. If I did interval notation, then I know I'm going to exclude that 27 here on this sort of graph. So that means it's going to end up breaking this up into 2 different intervals. One that starts at 2 and stops at 27. And then another one that starts at 27 and continues to infinity. Now I know at 2 I have a closed circle, which is perfectly okay. So that means I'm going to have a bracket around 2. But it's parentheses, always parentheses around infinity. But I know I cannot use 27, so it's not included. So I use parentheses around 27 and then have to incorporate the union. So again, the main idea is being able to plug them into each other. It gets a little tricky when you're dealing with domains. But the idea is the only restrictions are with fractions and square roots. The rest don't have any. So again, I wanted to do the examples that involve the restrictions because those are the most difficult to do. The ones that have no restrictions aren't as bad. So just keep that in mind. Make sure you plug them into each other. But sometimes some of the compositions they do doesn't involve the x. It actually involves using a number instead of the x. So here's what I mean. So let's say let's say we're given these functions. Let's say we have f of x is equal to x squared plus 2x. And g of x is equal to x minus 4. We're going to try to find first one. We're going to look for f of g of 6. So now again, I can write this the same as f, the way we were writing it before, g, but instead of x, I already have a value of x that I'm trying to do. So what this is, we're evaluating a composition, but before we're just using the x. So again, these both mean the same thing. So what I'm going to do, there's 2 ways to approach this. You can try to find what this g of 6 is, or try to plug it all in at one try. Meaning I'm going to plug the 6 into this x, and then plug it all in. Or you can try to find what g of 6 is. So that means everywhere you see an x for g of x, you're going to replace it with a 6. So right here, I'm going to put parentheses around my x, and then subtracting by 4. Because everywhere I see an x, I'm replacing it with a 6. Which this leaves me with 6 minus 4 is 2. So this is just a side note. So now, when I try doing f of g of 6, where I can replace that g of 6 with a 2, and now I'm just doing f of 2, meaning everywhere I have an x for my f of x, I'm going to replace it with this 2. Which this was, well, we know 2 squared is 4, plus 2 times 2 is 4, and that's going to be equal to 6. So that means f of g of 6, so I can put that. right here. So f of g of 6 is equal to 6. Hopefully I didn't confuse you too much with that, but let me try one more example. Hopefully I can recuperate from there. So let's just do g of f of negative 3, the way we were seeing it before, which this just means g of f of negative 3. Again, if you want, you can try to just plug the negative 3 into your f of x and then replace it all at once, or you can just, let me put a note here on the side, you can just try to find, oh, I scooted all the way down. You can just try to find f of 3 to begin with. Which I'm doing is everywhere there's an x for this f of x, I'm replacing it with a negative 3. So a negative 3 will go in here. A negative 3 will go in here. And that simplifies. Well, I know negative 3 in parentheses squared is 9. And then 2 times negative 3 is negative 6, which leaves me with a positive 3. So that means for this, oops, how all the colors mixed around. For this g, or this f of negative 3, I'm going to replace it with what I got for f of negative 3, which I got a positive 3 out of this. So that means everywhere I have an x for my g, so that's just here, x minus 4. I'm going to replace it with a 3, leaving me with a negative 1 as my answer. So again, these are much nicer. Maybe I should have started off with these, but sometimes I like to start with the more difficult ones and then end with easier ones. But the idea is you have to be able to figure out how that plugging in is happening. There, the number gets plugged in, but you're plugging in what g of x is for that value of x. So you're plugging in f of x at a particular value of x into the g. So stuff is still getting plugged into itself. It's just when you have the number, you can actually simplify it. Before we didn't have the number, we had everything in terms of x, and all we had to do was try to find if there's any restrictions to these functions after we do the composition of them. So let me give you some homework. Again, not too much, but try to watch these because I'm gonna test you on these on Monday. If I'm gonna send an email out later today. Later today is Tuesday, and to let everybody know when the next exam is coming. It's gonna cover more things. I'm gonna post more lectures up, and I'm gonna test you on all that together. But the final, I'm not gonna test you on everything. Whatever I teach next week is our last week. That's what's gonna be on the final. But this test that I gave you on Monday is whatever I can post up this week. That's what I'm going to test you on Monday. So let me give you some homework for this 2.8. Again, I'm going to come over a few more sections, but at the same time, I'm giving you, just like before, a couple of days to finish the exam. So even though I'm sort of including all this at the end, hopefully it gives you enough time to be able to do this. Just due to the nature of how everything occurred. But here, try doing a couple of these examples. Let's say number 9. Number 9 is good. Number 10. So again, some of this stuff is for what we did at the beginning with combinations, or operations with functions. I'm gonna jump to 19. Let's do 21. I think. Let's say 23. You have to put a little bit of thought into that one. And then 25 is fine with me. And then 25. That's not bad. Oh, and then do some difference quotient problems. So 33 and 35. So practice some of those difference quotients that we did. Lastly is doing some composition. So that would be 47. 47 is some of this stuff that I did right here, where you're plugging in the number, and it's not just, you're not looking for any type of domain or anything. So let me try 52. I'm just sort of jumping around here. Let's do 55 and 60. And then we do some compositions that involve you trying to find the domain. So just try to be able to do these. So let's do 65. Let's do 67. I'm gonna jump to 73. And what else do we have here? I'm just trying to see, sorry for the long pause, I'm just trying to see which other problems I should give you for homework. Let's do 75. And that should be good. I don't want to do too much, but I think those are pretty good to start off with. So try doing those, see what you end up with. Alright, if you have any questions, please go to my office hours or just email me and we can set up a quick Zoom session anytime. Again, I'm free all day, so please email me. I can send you a Zoom link if you want to meet up privately, one-on-one session. Please let me know. This is a 75. Sorry, it looks funny. Try doing some of these. Again, I'll be posting more videos up. And again, you have plenty of time for the exam. So again, it's open book, open notes. So hopefully, even though a lot of this information is coming quickly, hopefully you have enough time and resources to help you finish the exam. Okay, thank you. Bye.